Okay, so that'll be okay. All right. We are doing 2-7 related rates. Rates are what? Remember, derivatives go with slope, and slope gives us a rate. So does it at least make sense? Rates are going in this chapter, okay? Related means you got a couple things happening at the same time, but they have a relationship, okay? They're related. 2 or maybe 3 things are moving or flowing or something like that, but they are related. That's why we call them related rates, okay? Let's see, they give us a little example here. If we are pumping air into a balloon, both the volume and the radius are changing. Does that make sense? The radius of the ball is changing, or we'll call it a ball or a balloon. For right now, we'll just consider the balloons spherical, okay? We're not gonna get too in depth here yet. So the radius is changing, but also as it's getting bigger, the volume is changing. So those are the things that are going on, but they're related to each other. Okay, they're both part of this balloon. They're both part of as the air is going in. Okay. What else is there? The rates of the balloon are increasing, and the rates of increase are related to each other. Okay. So not only is the radius and the volume related, but their rates are related as well. In a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity. Don't worry about that so much. Oh, let's see, the procedure is to find, okay, so the procedure is to find an equation that relates the two things together. We got to figure out how are we going to relate volume of a circle or volume of a sphere, this balloon, to the radius of the sphere or the balloon. So the procedure is finding an equation to relate the two quantities, and then we're going to use the chain rule to differentiate both sides. This is kind of interesting, and I think it's in here somewhere. We take the derivative in terms of time. And because we're doing it in terms of time, and I know we're getting a little bit ahead, we got to see some stuff, but because we're doing it in terms of time, that's why we have to use the chain rule. Okay, so we'll talk about that. All right, so let's take a look at this first example. All right, let's see, can we see it? Okay. All right, so air is being pumped into a spherical balloon. So we're going to consider it a perfect circle, okay? So that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when its diameter is 50? So step 1 says we got to figure out an equation that relates volume and diameter or radius, either one. So that is, does anyone know what that is? That is a formula for volume, because guess what the formula for volume is? Volume is equal to, for a sphere, it's 4/3 pi r cubed. Do you see how this one formula or equation involves volume and radius or diameter? Okay, those two we could, because we can always adjust diameter to radius. So we found the one equation that both, how they're related, volume and the radius. Okay, step 2 says then plug in any constant values or equal values. We don't have that in this problem, so we'll talk about when that pops up. Then step 3 says, let's see, do we have? No, we're good. All right, so step 3 says take the derivative. But here's the weird part. We're going to take the derivative in terms of time. Taking the derivative, because we want to know at 1 minute what's the volume, what's the radius, or seconds. At 2 seconds, what's the volume, what's the radius. So we really have this third component in here that is time. So we want to take the derivative of v. Well, the derivative of v is 1. But we have to think of it as a quantity because inside there is time. And so its actual derivative is 1, but then what do we do when we have a quantity? We have to take it times the derivative of the quantity. So we're going to write this. We could write this as v prime like that, but I kind of like to write it like this because we're doing the derivative of volume. But remember, we're actually doing it with respect to time. T is time. And that reminds us that that's why we have to literally, because of this t, that's why the answer isn't 1. We have to take it with respect to time. All right, what's the derivative here? This is just a number. This is just a coefficient. So I'm going to roll it down and subtract 1. So here's my equal sign. I got 4/3 pi times 3 r squared. But I'm not taking the derivative of r. I have to think of r as a quantity because I'm actually taking it with respect to time. So if r is a quantity, what do I have to multiply it by? The derivative of r, and I'm just going to write it like this. The derivative of r, I'm just going to remind myself that it's with respect to time. Okay, you could put r prime, that's okay. But it kind of reminds you, why did I have to do this in both cases? Because I'm actually doing it with respect to t. That's kind of weird because it doesn't really show up. But you have to think if the balloon is increasing, what else is involved? Time, right? That's kind of what makes it increase. As you're filling it up, time is going by. All right, now we're in good shape. We can simplify here. Let's get rid of the 1. Let's just rewrite this. dv over dt equals, do we see how the 3's cancel? And so we just have 4 pi r squared and then dr dt. What is dr dt? What is dr dt? The rate of the, what did you say? I think you said it. I just didn't hear it. No, say it. The rate of the radius. The rate of the radius. Yeah, with respect to time. Yeah, that's the rate of the radius depending on the time. And dv dt is the rate of the volume. Okay. Good. Okay, so now we just plug that in. I think we're in really good shape. Okay, so now the diameter is always increasing, but the moment in time that we want this, what is the diameter? The moment in time that we're looking for our answer, the diameter is 50. Okay? So we're just going to plug in 25. Do we see where the 25 is coming from? That's just half of the diameter. And then what else do we know? We only have we have 2 variables. We have to leave 1 of variables because that's what we have to find. How fast is the radius? How fast is the radius? So that means we're looking for dr dt, the rate of the radius. So they better tell me something. Do they tell me something about the rate of the volume? The volume increases at a rate of 100. Now we just got to solve that for dr dt. Let's see. So if we do 25 squared times 4, that should give us 2,500. These answers aren't that pretty. So that, do we see where that's coming from? 25 squared and then times 4. And then how am I going to get dr dt by itself? This is just multiplication, so we're going to divide. Divide by the 2,500 pi. Okay, we can cancel the zeros there, right? The pi is on the bottom. So it'd be 1/25 pi. Let's leave a little bit of space for units. dr dt. Does anyone want to try units? It's a rate. The rate of the volume was centimeters cubed per second. This is a radius, so it's just a length. So it is centimeters per second. You could write centimeters per second. It kind of tricked us just a little bit too, because I wanted to make sure it does say how fast is the radius, but then they did give us to it as a diameter. But the question says radius, so we're in really good shape. We don't even have to transfer back to something like diameter. And you type, so make sure you type it in like that on the website. I think there's one that says to round, but otherwise I think the rest, go ahead and type it in terms of pi. All right, what do we think? Let's try another one. Look, compared to some of our problems, they're not too long, okay? So take your time on the setup. Don't hesitate to read it 3 or 4 times, because once you get it set up, I think it'll go pretty quick. All right. A cylindrical tank. Do we know what that is? Cylinder, like a can of soup, but this is big tank. I think it's holding gasoline, okay? So a big cylinder. You don't have to draw a picture, but can you see any of that? All right, so a cylindrical tank with radius 8 feet is being filled with gasoline at a rate of 4 cubic feet per minute. How fast is the height of the gasoline increasing? Now don't panic. I know years past they're always like, I don't know what the formula is. Because what's the first step? Find a formula that relates the two. You'll kind of see that the same ones will kind of keep coming up. And I'll try to do them pretty straightforward for the test too. Okay? But if you get stuck there, then ask. Okay. All right, so cylindrical tank, what are they talking about? They're talking about radius. They're talking about height. And they're talking about filling up the tank. What word is that? Filling up the tank. Filling up the tank is volume, okay? So what's the formula for volume of a cylindrical tank? You know the formula for volume of a cylinder? Area of the base times the height. Area of the base times the height. So area of the base, it's a circle, so pi r squared times the height. So again, so once you kind of see that for all cylinders, that's pretty much what you're going to use. Okay, now does anyone see a little bit of a problem here? How many variables do we have? 3, okay, so that's a little bit of an issue. Sometimes it's going to stay 3. I think in our next example, it's going to stay 3. So we'll have to deal with that. But here's where, and I know you guys don't have this paper, but here's where step 2, plug in any constant values, okay, not rates, just values, okay? Or, and there's another time where we'll use equal values. Even though stuff is being filled up in this cylinder, is there one number that is never going to change? Think of gasoline being filled up in here, or water, or whatever you want. Is there one number that's never going to change, no matter how much gasoline is in there? What'd you say, Jeff? Not that, well, I like it. No, I like it. Actually, let's go with the area. Yeah, the area of the base, right? I like that. Yeah, the area of the base, pi r squared. What's that radius that's never going to change? That's the word I was thinking. Just saying the word radius is never going to change. But the area of the base, that's fine. Yeah, I like it because that includes the radius. The radius is always going to be 8. So let's take advantage of that. That's what step 2 is. Now let's go back up here. How come I didn't put 50 in right away? 50 was the diameter. Was the diameter changing in this problem? Yes, right? As I fill up a balloon, the diameter is going to be changing. And so that's why I didn't plug it in, or the 25 for the radius. That's why I didn't plug it in until after I took the derivative. Okay? So if it's not changing, you put it in at the beginning. If it's a number that's going to be changing and we just happen to say stop, then you have to put it in after the derivative. Does that make sense? All right, so this 8 is staying the same throughout the whole problem. So I can put it in right away. All right, we'll do more. We'll kind of talk about that, but that's kind of one trick there. You have to decide, is it changing? Then I have to wait. If it's not changing, I put it in right away. So volume equals, so I put it in before, and that's 8 is the derivative. So I do 8 squared. And that's really nice because, one, it got rid of stuff, right? And that's not too bad. It got rid of a variable, right? So 8 squared is 64 pi. Let me see, besides a little cylinder. Okay. Now we're ready to go. Now we're going to take the derivative. Okay, with respect to time, with variable that is kind of out there, it makes sense, but we never see it. That's the hard part. Well, we're going to do it with respect to time. So the derivative of v is 1. But because we have to think of v as a quantity, we're going to do then the derivative of that quantity, dv, with respect to time. Okay, here we're going to do the derivative of h. So we're going to roll it down and subtract 1. So what's the derivative of 64 pi h? Just 64 pi. But we have to think of h as a quantity. So we have to take it times the derivative of the quantity, which would be dh in terms of time. Okay. So we rolled it down, subtracted 1, but we have to think of, and it's kind of nice, you don't even, when we did implicit, you had to remember x no, y yes, right? Here, every variable, because we're actually doing it with respect to time, which isn't even on our paper. Oh, let's see. Anything else? No, I think we're good. So now, what is this guy? This is what? This is being filled with gasoline at a rate of 4 cubic feet per minute. How fast is the height? So which one am I finding? dv or dh? How the height? Okay, so I'm looking for dh. That's the rate of the height. So what is this 4 cubic feet per minute? That's the rate of the volume. Okay, that's the rate of the volume. So 4. Good. And then how do we solve that? Just divide by 64 pi. 64 pi. Can we see any of this? Yeah, okay. And that's the answer. We can reduce, okay? WebAssign will take that, but we can reduce. 4 goes in there once, and then 4 goes in there 16 times. And then don't forget pi is actually on the bottom, so just be careful when you're typing it into WebAssign. We're not used to that. And that's it. That's the rate of the height. Does anyone want to try units? The height is just a length, so it would be, instead of cubic, it would just be feet per minute. You could even write it like this if you want. Usually, for some reason, units we usually write on one line, but you don't have. That's the same thing as feet per minute. Okay, let's try. Should we try another one? The biggest thing is that equation. If you can come up with that equation. right, the base of a triangle is increasing at a rate of 2 centimeters per minute. Height is increasing at a rate of 4 centimeters per minute. At what rate is the area changing when the base is 20 and the height is 32? So they're talking about a triangle. They're talking about a base. They're talking about a height. They're talking about an area. So we're talking about a triangle. We're talking about a base, a height, and an area. And I know you've only read it one time, but any ideas, the formula that we would use for that? What relates all that together? Yeah, area of a triangle, right? Area of a triangle. You could do base times height divided by 2, or you could do 1/2 base times height. Okay, see how we got the base in there, we got the height in there, we got the area in. Some equation that relates the two. Usually if they're talking about volume, it's the equation for volume. If they're talking about area, it's the equation for area. Now, step 2 is, because we have 3 variables. Step 2 says, is there something that's never changing? Just like the radius, remember the last problem, the radius was 8, it never changes. But I think here, everything is changing, okay? The base is always changing. Eventually, we want to say stop, and we're going to use 20. But if it's changing, we can't use the 20 until after we take the derivative, okay? The height, does it say anything? The height is increasing. The height is increasing. So that just is telling us the height is changing. So eventually I'm going to use a height of 4, but I have to do that after we take the derivative. Okay? Everything's changing here, so we can't fill in anything. So that means we have 3 variables. How are we going to do the derivative of this side? Product rule. Product rule. Okay. So let's see. Let's go ahead and set this up. Let's do this. Let's do f, instead of x, let's do f of t. F of t is going to be 1/2 b. What is its derivative? What's the derivative of 1/2 b? 1/2, but because I'm taking it in terms of t, I kind of like this. You kind of get to see a visual. Because I'm taking it in terms of t, that means this has t's in it, but I don't know where they are. So I have to do the derivative of that quantity. So it's going to be dB in terms of t, dt. Okay, let's try that for g. Okay, so what is g of t? G of t is h. What is its derivative? Normally we would say 1, and that's right, but you have to think of h as a quantity because it's got t's in it. So it's going to be the 1 we won't have to write. It would be then dh dt. Yeah.
Why don't you keep the 1 after?
So you don't want to do it to both, right? You mean like why didn't the 1/2 go with the h as well? Because you're just multiplying. I don't want to write. Because you're just multiplying 3 things. Like if you did the 1/2 to the b and then the 1/2 to the h, then you're really saying you have 1/2 b times 1/2 h. Do you see how that is? So we just want to figure out a way to break this up. You could, if you wanted to, you could have done b and then you could have done 1/2 h. We really only want to think of this as 2 things being multiplied. So we'll just stick the coefficient with one of them and then we got the other. Does that make sense? That's a good question. That's good. Yeah, and it doesn't help that it's a 1/2, but just think of this as like think of it as like 7BH. You'll just group this together as one and then that. Okay. Good, good, all right. Okay, so what's the derivative of A? Derivative of A would be 1, but we have to think of it as a quantity, so we're going to write dA dt. Then on this side, we have to do the first, oops, we'll do t's. First times the derivative of second plus the second times the derivative of the first. All right, so this guy's going to stay dA dt. F of t is 1/2 b. And then the derivative is, now be careful, the derivative is dH dt. A lot of kids last year said, why aren't these two matching? But it actually makes sense that these two aren't matching, right? Because remember, you got to do the product rule. So it's f of x times the derivative of g. Okay? And then plus g times the derivative of f. I might need extra paper anyways. Okay, so let me just cover this up. You guys maybe can sneak it on here. Hopefully you wrote a little bit small. I try to leave some room, but. Okay. Do we have the rate of the area? Look at the question. At what rate is the area changing? Okay, so that's our variable. That's what we're trying to find. Beautiful. That's okay. That's a piece of cake. 1/2. What is our base? Now our base is always changing, but when we say stop, what's the length of our base? B is the base. 20. Beautiful. Okay, so I'm right here. Then what is this calling for? dH dt is calling for the rate of the height. Remember, derivatives, you always have to put in a rate. Derivative is always going to correlate to a rate. So we actually need the rate of the height. Do we have the rate of the height? Height is increasing at a rate of 4. All right, what is the height? Now the height is always changing, but we want it right when the height is 32. Height is 32. That's times 1/2. And then this is the rate of the base. Hopefully they tell us. It's kind of weird. Yeah, do you see that? The base of a triangle is 2. Or what does it say? The base of a triangle is increasing at a rate of 2. There it is. Good. All right, so that is 2. That's just a matter of plugging it in. Right. Let's see. So that gives us what? 40 and 32. This would give us 80 divided by 2, or if you want to do 10 times 4, however, whatever. It doesn't even matter. Those cancel. That's nice. 32. So it would be 72. So you probably could have fit that on here. I just wanted you to kind of see it going down. Anyone want to try the units? Area would be squared, so centimeters squared per minute. Yeah, just kind of look, like I looked here, the height was a length, so it was only centimeters, but it was per minute. So area is just going to be squared. All right. All right, let's try the next. Remember, they're fairly short. 4 is pretty short, so remember, it's okay if you have to read it a couple times. All right, a pebble is thrown into a pond and the ripples spread in a circular pattern. if the radius of the circle increases at a constant rate of 1 meter per second, how fast is the area of the circle increasing when the radius is 4 meters? Okay, so there's a lot to read, but we had to come up with circular, radius, area. What's the formula that relates it all together? Area of a circle. Right, and again, if you don't see it right away, don't completely panic. You might have to read it a couple times, okay? And if it absolutely doesn't come to you, we'll figure it out on the test. Figure something out. Area of a circle, pi r squared. Okay. Now just be careful. I don't like this phrase constant rate, because remember we talked about if something's constant, you can plug it in before. You can never plug in a rate before, because a rate has to go in for a derivative. So even if the word constant goes with the word rate, you gotta wait till you take the derivative, okay? Because rates and derivatives go together, so you have to take the derivative. So I think usually if we have two, well, yeah, I think usually if we have two variables, there's probably nothing constant, right? As far as an individual value. All right, so what are we gonna do? We're gonna take the derivative of A, but with respect to time. So what are we gonna write? Technically 1, but then we have to take the derivative of the quantity, dA dt. And if you just write A prime, that's okay. For me, it just kind of reminds me that, oh yeah, I did that as a quantity because I was actually doing it with respect to time. All right, pi is just a number. How are we going to take the derivative of pi r squared? Roll it down, subtract 1, so 2 pi r, but we have to think of r as a quantity. So times dr dt. Are we okay with that dr dt? Roll it down, subtract 1, but everything's a quantity because we're actually doing it in terms of t. So in here and in here are times. It's kind of weird. Okay, then we're good. What, let's see, so what are we trying to find? How fast is the area of the circle increasing? Which one's that? How fast is the area? That is the dA dt. That's the rate of the area. It was always changing. The radius was always changing, but I want the rate of the area when the radius is what? When the radius is 4. Yep. You see how that's always changing, and I couldn't put it in up here. But the moment in time that I want this rate, I do have to know the radius, which was 4. Okay. Now, do we have anything about the rate of the radius? If the radius is increasing at a rate of 1 meter per second, so that goes in for what? That's a rate of the radius. I'll get in. Good. So this one, the rate dA dt is equal to 8 pi. Let's see. Area. So the radius was meters per second, so area would be square meters per second. And WebAssign's nice. I think they give you the units, but sometimes, like I said, it just helps to kind of so you understand what you found. All right, this one's maybe a little bit harder because this one is harder. You might need more room. Oh, and I know this one's harder because you don't have a picture. I think I got this from a book. They may have had a picture. So let's try it. At least you'll see what the picture looks like. Oh, I know. I think this is also on the homework, and they do give you a picture. So that'll help too. All right. A rope is attached to a boat at water level, and a woman on a dock is pulling on the rope at a rate of 50 feet per minute. if the woman's hands are 16 feet above the water level, how fast is a boat approaching the dock when the amount of rope out is 20 feet? Okay. So we have this boat, and remember, they're going to give us, so we got water. We got this lady standing on a dock, okay, and her hands or whatever is 16 feet up. So this is where the rope is, okay? She's standing on a dock plus like her body, wherever that would go, the dock height plus maybe her body height up into her hands where she's pulling. What is this? Do you see how that is 16 feet? She's standing on wherever to her hands is 16 feet. Can we see the picture? Okay. Okay, and then the rope goes, we'll put the boat, I don't know, we could put the boat here, but the boat, and again, this is maybe, the boat goes to the water level, or I'm sorry, not the boat, the rope goes to the water level. So the rope goes from her hands and they put it to the water level. So what did we just draw? Triangle, yeah, and that's why they had to go to the water level. So it is what it is. But all right, so we have a triangle. That's 16. Now, how fast is a boat approaching the dock when the amount of rope is 20 feet? The 20 is constantly changing, right? Because she's pulling it in. But at the moment in time where we want our problem, it's 20. What about this height? Is this height ever changing? No. So keep in mind, this guy's going to be a constant. We're going to put this in right away. The 20, sometimes I put it in parentheses, that's always changing, and we'll use that after the derivative. But the 16 is never changing. So we can actually use that right away. What else? We're talking about how fast the boat is approaching. So they're talking about this side. They're talking about this side. And we're at least doing something with this side because we're talking about how fast the boat is approaching. Hopefully, if they built the dock correctly, this is a right angle. So what would involve the three sides of a right triangle? A squared plus B squared equals C squared. That's the relationship. We're trying to tie in the three sides. And I know this one's kind of hidden too, but eventually we're going to find that one. Is this side always changing? As the boat is coming in, the length of that side is always changing. Okay? So we have to hang on to that anyways. But we're going to do A squared plus B squared equals C squared. So a lot of times with triangles, it's either area or if we're just talking about the sides, hopefully, the only thing is it has to be a right angle. You have to make sure that it is a right triangle before you use A squared plus B squared equals C squared. What else? Oh, what we can plug in. So we got our relationship. What can we plug in though? What is never changing? The 16. So let's at least plug that in. A squared plus 16 squared equals C squared. And if you have the A and B reversed, that's okay. Don't worry about that. You just have to make sure C is the hypotenuse. All right, and 16 squared is 256. All right, I think we're ready to go. That 16 is never changing, so we got to plug that in right away. The 20 is changing, so we have to wait and plug that in. I kind of like this problem because now we see that and we see how the 16 can go in right away, but the 20 has to wait. So that's a good problem to go back to if you're trying to figure out, do I put it in or do I wait? Do I stay or do I go? All right, so, okay, who wants to try this? What's the derivative of A squared? 2A dA dt. Yep, 2A dA dt. And even better, who wants to do derivative of 256? 0, right? He's gone. And then what's the derivative of c squared? 2c dc dt. 2c dc dt. Okay. Where is 20 going? I'm kind of looking like I have the 20 marked. The 20 is the length of the rope at the moment in time. So 20 is C. Since I'm over here, do we have anything about the rate of the rope? Since we're right here, this is the rope. You could also do like R if you wanted to for rope. Don't forget that this is the rope. Do we have anything about the rate of the rope? She's pulling the rope in at 50. Yeah, so this is 50. We're looking for how fast is the boat approaching the dock. So that is the rate, which is great because I have a rate available. So that's my variable. This is, oops, this is where it gets just a little dicey. This guy's 2. The problem is I need A. But thanks to the Pythagorean theorem, we can go use it. We're going to go off to the side. Maybe I can sneak it in down here. We're going to do, because at the moment in time, I can use 20. So we're going to do a squared plus 16 squared equals 20 squared. And then I can go find A. Oh, oh, good call, good call. There we go. But now is it going off the other side? No. Good. So yeah, so let's back that up. So we can now use 20 because now we're into the moment in time. So now we're going to do a squared plus b squared equals c squared. We're going to do a squared plus 16 squared equals 20 squared. So you have to go find, that's why this one's a little bit harder. So a squared plus, what is it? Is it 256? Oh yeah, we already did that, right? 256 equals 400. Subtract 256 and take the square root first. Can we even see any of this? Yeah, okay, you can see that. What does that give us? Yeah, 140, perfect. Both are right. Yep, 144, which gives us then 12. Good. Okay, are we okay? To undo the square, take the square root, which is 12. All right, so now we can fill that in. So that was a little bit trickier, but now we're good to go. Multiply that, so that gives us what? 24 dA dt. And then that gives us what? 22,000 divided by 24. Is that right? Do we have enough of that? dA dt should be, did anyone get it? Doesn't go in there either, so don't panic. What did you get? Yeah, perfect. 83. So this might be the one on the homework where they tell you to round. So just look if they say rounded 2 places or something like that. Good. It's just the length. So this would also be feet per minute. Now we're pushing. All right. So the number 7, I wasn't even going to do. It's a little crazy. And number 6, when you get to the gravel one on your homework, we'll just save that for Monday. And I'll take that into consideration. I haven't put Monday's homework up, so I will make sure maybe I'll make Monday's one less then. So we'll go ahead. So make sure you hang on to this. We'll do 6, and then we'll do a few more on Monday. So on Monday, you'll be able to finish this homework assignment, and then we'll maybe have maybe 2 or 3 more. All right. So do as much as you can on the homework tonight. You should be able to do them all except the gravel. Okay. A problem like 7 is not even on the homework at all. I ended up taking it off. Okay. I can maybe do that for extra credit. Maybe I'll sign it Monday, like for extra credit. If you want to try 7, it's pretty tricky, but you could try it. You could do it on separate paper, turn it in, or we could walk through it if you have some questions. But 7, there is not one like 7 on the home. And then 6, hang on to a gravel problem or sand problem. Hang on to that for Monday. All right. Good. Oh, no. Did I forget to?